All right, let's get started. So today I'll finish the discussion of exploration, and then I'll start on a new topic, which is called transfer learning. Some class notes. So homework 4 is due today. That's the last one, and I imagine that the room is a little sparse because many of you are probably watching at home and finishing it up. There is a little bit of a not a typo, but somewhat unclear phrasing in one of the questions on homework 4. So if you already did homework 4 and it works great, that's fine. If you have a little bit of a problem with the number of iterations and you're finding that things are increasing very slowly, be sure to read the note that was posted on Piazza this morning. There was just the use of the word iteration was a little unclear in the question, and some students interpreted that correctly and some misinterpreted it a little bit. So if you're having things improving very, very slowly, read that note and make sure to take a look at that. Okay, so let me first, in the first half of this lecture, I'll finish up the discussion of exploration. So to that end, let's first recap some of the stuff that we discussed on Monday. So we talked about how there are kind of 3 broad classes of exploration methods that we'll cover. The first one, which we discussed in detail, is this optimistic exploration approach, where you basically assume that a state that you haven't seen very much before is a good state, so you sort of assume optimism unless proven otherwise. And this typically requires some kind of estimation of a state visitation frequency or some kind of estimation of novelty. And it's typically realized by means of an exploration bonus, so adding something to your reward function that is not actually the thing you want to accomplish, but incentivizes your policy to go to places that are new, places that it hasn't seen before. Then in the context of bandits, we talked about Thompson sampling style algorithms, and we'll talk about these more in the context of deep RL today. So these are methods that learn distributions over something, over maybe Q functions or policies or something relevant to your MTP, then sample from that distribution and act according to the sample. And then in the context of bandits, we talked about information gain style algorithms, which reason about the information gain that you get from observing something new. So in the context of deep RL, this will mean information gain from visiting new states. And we'll talk about a few methods in that category as well. So let's recap the optimistic stuff. So when we talked about optimistic exploration in deep RL, we talked about this notion of pseudo counts. So one of the ways that you can quantify the novelty of a state is by counting how many times you've been in that state. But in very large or continuous spaces, you might never see the same state twice. So you can't directly count the number of times you've seen that state, but you can use something called a pseudo count. And that consists of fitting a model to all the states you've seen so far, a density estimation model, p theta of s. And then when you collect a new sample, you update the model using that new sample, and then you can use the new model and the old model, you can compare them to get a pseudo count, which is a number that looks like a count but isn't actually a count. And that can let you produce reasonable pseudo counts even for states that are not exactly identical to any of the states you've seen before. And then you make your reward function be your actual reward function plus an exploration bonus. The bonus is based on the pseudo count, and then you repeat. So this is what we covered on Monday. And we talked about how you can get the pseudo count by solving a system of equations, by basically saying that, well, if it was a count, then incrementing it by 1 is the right way to get a new model. So let's use our new model and recover what the n hat and little n hat should have been. So this was in the discussion of pseudo counts on Monday. And then we talked about a few other ways that you could do optimistic exploration using things like hashing and other choices for the density models, like the EX2 model. But for today, let's continue this story and let's talk about the next class of exploration algorithms, which are posterior sampling or Thompson sampling style methods. So to remind you about the discussion on bandits, when we talked about Thompson sampling, basically the story is that you have some set of parameters, theta 1 through theta n, that define the behavior of your bandit. So these might be the parameters of the distributions according to which the bandit emits the rewards. And you can frame the bandit problem as a POM-DP problem, as a partially observed Markov decision process, where the state consists of these thetas, and your belief state consists of a probability distribution over those thetas. So if you're very Bayesian and your very Bayesian algorithm is exploring this bandit, it might fit a belief p hat theta 1 through theta n. So in Thompson sampling, the idea was that you would somehow fit this distribution p hat theta 1 through theta n, and then when it comes time to act, you would sample a particular set of thetas from that distribution, and then pretend as though those were the true thetas and act optimally with respect to that sampled model. So that was Thompson sampling for bandits. So now, can we extend this idea to deep reinforcement learning? Well, there are a few questions we have to answer. What do we sample? Meaning, what are the thetas in the case of deep reinforcement learning? And how do we represent the distribution? How do we actually represent p hat? So in the bandit setting, the thetas this is not quite right. The p hat is your belief over the thetas, and your thetas determine the distribution over rewards. Not p hat theta, the thetas themselves determine the distribution over rewards. So a little typo on the slide there. So what's the closest to a distribution over rewards in a deep RL setting? Well, in an MDP, the analog here is not actually the reward function, it's actually the Q function. Because in a bandit, once you know the reward, acting optimally is easy. You maximize over the A's with respect to the reward. So in an MDP, you don't maximize over the reward, you maximize the Q function. That's how you choose the action. So the analog to this thing in an MDP setting, a very reasonable analog at least, is actually the Q function. It's the thing that once you have it, you can just act greedily. So in a bandit, once you know the reward, you can act greedily like this. And in an MDP, once you know the Q function, you can act greedily. So in a sense, the Q function encompasses your strategy. Once you have the Q function, you have the actions. So let's do posterior sampling over Q functions. The way that we can do this, and this is discussed in more detail in this paper by Ian Osman and collaborators called Deep Exploration via Bootstrap DQN, is in step 1, you sample a Q function Q from your distribution over Q functions. And we'll talk about where this distribution comes from in a second. Step 2, you pretend this Q function is a true Q function, and you act according to that Q function. So if you're doing Q learning, maybe you do epsilon greedy as your policy, and it's epsilon greedy with respect to the sampled Q. And step 3, once you've acted according to that Q function, you update your distribution over Q functions P of Q to incorporate this new evidence. And then you repeat. And this third step, in a Q learning algorithm, this third step is quite nice because Q learning is already off policy. So you don't really care about the fact that you sampled the Q and then acted according to it here, because you can still update the entire distribution using samples from one particular Q function, because Q learning is off policy. So this third step for Q learning in particular is quite nice. OK, so this is a very high-level overview. I haven't really gone into the details of how each of these steps is implemented. So let me drill down into this a little bit more. And the first thing that I'll drill down into is how we can actually represent a distribution over functions. So Q functions are functions. They map from states and actions to scalars. So we need to represent a distribution over functions somehow. How can we do that? There are actually a number of choices that we can use. There are a variety of different Bayesian neural network methods that can allow us to do this. But one very simple way to do it, which is actually very general in terms of the class of models that it can accommodate, is what's called the bootstrap. So let me summarize this very briefly. You might have learned about this in a machine learning class. Very simple technique for getting a distribution over functions. And it works like this. If you have a data set, D, what you can do is you can transform this data set D into n different data sets that sample from the same distribution as D. And the way that you do it is you resample D with replacement. So that means that, let's say you want a data set of size m, then m times, you generate a random integer between 1 and m, take the corresponding data point from D, and put it into the new data set. So that means that the distribution over points in each of these new data sets, D1 through Dn, is the same as in the original data set, but the particular data points themselves might be different. So some data points might be repeated multiple times, and some might not occur at all. And it's important to resample with replacement. So this is, essentially amounts to putting an integer count on each of the data points. Does this idea of resampling with replacement make sense to everybody? Does anyone have any questions about it? OK. So this way you get n different data sets that are still from the same distribution. And then what you do is you train n different models. And for each model f theta I, you train it on the data set di. So each of these models is trained on data from the same distribution, but on a different data set. And then if you want to approximate sampling from the posterior, this should actually be p theta given d. What you instead do is you sample an integer from 1 to n and use the corresponding function f theta I. So this picture, this is actually from the Ian Osman paper. This is on the left. So what this picture is showing is a regression problem. So you're mapping from one variable to one other variable. So on the x-axis the input, on the y-axis the output. And this left picture shows a distribution over functions learned by a Gaussian process. So a Gaussian process is a non-parametric Bayesian model that allows you to learn distributions over functions. It gets very intractable if you have too many data points, but it's a nice, like in really small problems, it's a nice kind of gold standard. So you train your Gaussian process, you visualize, and that tells you what a good distribution should look like. So that's kind of our gold standard. And what this visualization shows is the red line, that's the true function. And the true function is corrupted by noise, of course. So there's some noise here. The dark black line, that's the mean of the Gaussian process. So that's what the Gaussian process thinks is the average function. And these gray shaded intervals, those are showing 1 and 2 standard deviations around that function. So you can think of these as a measure of uncertainty. And then you can sample functions from this distribution. And it does something very reasonable. So these black dots, those are your data points. As you get further away, the variance increases. And here in the middle, there's a lot of noise, so there's a little bit of variance there too. On the right, you see the same exact problem solved using neural networks, an ensemble of neural networks trained with Bootstrap. And on the tails, it behaves a little differently. So on the tails, it kind of explodes. But in the middle, it actually looks very similar to the Gaussian process. So there's a little more variance here in the middle. It's a little tighter over here. So the Bootstrap is giving sensible uncertainty estimates. And the intuition for these black regions is basically, if you fit multiple models, and those models all agree, then your variance is small. If you're far from the data, they'll all overfit, but they'll overfit in different ways, so they'll all disagree, and that's why you get high variance. Yes?
Do you intend to use an ensemble over all of your n submodels, and B, why not just sample all of D with n different models, but with different seeds?
So actually, this is a very good question. Why not train on just D and use different random seeds for the models? In fact, if you do that, you get pretty much the same answer. And that's actually what's actually done in the paper. So the actual Bootstrap method requires you to resample your data set. And the reason for that is that the way that you fit f theta I in the theory is assumed to be the minimum error fit to the training data. So if you have a convex optimization problem, you'll actually get f theta I that minimizes training error on DI. Neural network optimization is not a convex optimization problem. And in fact, if you do it with SGD, it's in fact a stochastic optimization problem. So in practice, if you use a different random seed or a different initialization for each f theta I, you can actually just train them on the initial data set, and you still get a lot of variability between the models in the ensemble. So in order for the theory to really pan out, you need this resampling with replacement business. But in practice, you can actually get decent results if you don't even resample and just initialize your models with different random seeds. And that's, in fact, what's actually done in the paper. So they go on about how you need to resample, and they say, well, actually, we don't resample because we have neural nets. So a little anticlimactic. But it's still good to understand the theory behind this. OK, there's actually another issue, and there's another corner that we can cut. So training n big neural nets is actually kind of expensive. Perhaps we can avoid it somehow. So a little optimization, which is not necessarily theoretically motivated, but seems to work reasonably well in practice, is to not actually train n completely separate neural networks. If your networks are, for example, big convolutional networks that are processing images, maybe images from the Atari games, instead of training n networks that are completely separate, you can actually train one network with many heads. So for example, if you have 2 or 3 convolutional layers and then 2 or 3 fully connected layers, the different heads might have different fully connected layers, but they share the same convolutional layers. So then this can be computationally a little bit more manageable to fit. So you can actually have one network with many heads instead of n completely separate networks. OK, does anybody have any questions about the Bootstrap, how we can do it with neural nets, and so on? OK, so now let's go back to exploration with posterior sampling. So we can use the Bootstrap, we can build our distribution over Q functions, we can sample from that distribution. Why does this work? Why is this a good idea? So if you do a naive exploration strategy like epsilon greedy, random actions can oscillate back and forth. So you might take one action. Let's say you're playing the game Sequest. So in this game, you have to control a little submarine and destroy the ecosystem by shooting the fish and pick up the divers. So if you do epsilon greedy exploration, you can get some pretty silly action sequences. You might turn the submarine left, then turn it right, then turn it back left. That's just never useful. So it'll give you some diversity, but it won't really cover the space evenly. So covering the action space evenly with a near uniform distribution is not the same as covering the state space evenly, because random actions can just cause you to go back and forth. If you explore with a random Q function, you're kind of committing to a randomized but internally consistent strategy for an entire episode. So a random Q function, even if it's not a very good Q function, it's never going to do silly things like go to a particular state and then leave it and go back again. Because it's forced to commit to a strategy. Even if it's not a good strategy, it's at least a strategy that's internally consistent. So it might, for example, choose to consistently move the submarine upward at random points in time, and that could be good exploration here because it turns out that if you surface a submarine, you replenish your oxygen, which is a very good thing to do. So if there's one Q function in that ensemble that surfaces the submarine, then you'll eventually sample that. Whereas if you're randomly sampling actions, it's exponentially unlikely to surface a submarine because you have to press the up button n times in a row. So, okay, that's sort of the story for why sampling Q functions might be better than sampling actions. Does it actually pan out in practice? So these comparisons, the red curve is the bootstrap DQN, and the green curve is just naive epsilon greedy exploration. And kind of is the story. So it helps a little bit. This one is Montezuma's Revenge. It's a flat line for everybody. So it doesn't seem to help quite as much as the count-based exploration, as these optimistic exploration bonuses, but it gives you a little bit of a bump. So what are the trade-offs with these kinds of methods? Well, one really good thing about these methods is that there is no change to your original reward function. So you don't need to worry about choosing an exploration bonus, designing a probabilistic density estimation model, tuning the weight on the exploration bonus. The reward function doesn't change. You're still optimizing the same exact reward function as you had before. So in that sense, it's quite a bit simpler, less fuss. But the downside is that very good exploration bonuses will typically do better than this method, at least as far as the results that are in the literature. And that I think gives a sort of a reasonable intuition for the trade-offs. So quite principled, quite nice method. Very nice that you don't have to change the reward function. You're still solving the same RL problem as you were before, but the gains are a little more modest. OK, does anybody have any more questions about posterior sampling for exploration in deep RL? Yes?
This one has lower sample efficiency than the bonus method because it has to run the Q function for the entire episode, right?
So yeah, good question. The question was, could this have lower sample efficiency because you have to run the Q function for the entire episode? The way the algorithm is actually implemented is that you still do regular Q learning. It's just that you're updating all of the Q functions in parallel. So every time you sample a data point, you draw batches from your replay buffer, different batches for every Q function in the ensemble, and update each of the Q functions in the ensemble. The only thing that actually changes in the algorithm is how you choose your actions. So the training, like the different Q functions are basically unaware of each other. They're just drawing batches from the replay buffer and training. The sampling strategy does change. The sampling strategy works as following. You still do epsilon greedy, but for every episode, an episode here means between when you lose a life, you choose a Q function from your ensemble, and you keep using that Q function. So it's sort of, you can think of it as like a superset of the standard Q learning algorithm. Does that answer your question, or, OK? Yes?
So in Bandit-Thompson sampling, it said we sampled the I guess the action, the plan based on the there was a distribution of reactions that was weighted according to what we thought their reward would be. But I guess in this one, is there an analog comparing how giving a weight to each Q function, or do we just pick uniformly at random?
Yeah, so this is a good question. So there's two parts to the answer here. First, in the Bandit-Thompson sampling, you're not actually choosing actions with probability proportional to their optimality. You're choosing a model from your model belief, and then under that model, you're just choosing the best action, deterministically. And you're doing the same thing here. You're choosing a model, which in this case is a Q function, and then acting however you would act with respect to your model. So you pick the model, and then you just do whatever you were otherwise going to do, which in this case is epsilon greedy. Now, do you weight the models in any way? The answer is, in this method, you don't, because it turns out that the bootstrap is an unbiased estimator of the posterior distribution over models. So the reason that you don't weight them is because the bootstrap is supposed to just do the work for you.
Is there a reason that to use the same Q function for the entire episode instead of like switching?
Yeah. So why should we use the same Q function for the entire episode? The reason that we don't want to switch all the time is we'd like the agent to have the opportunity to follow a consistent strategy. So let's say that you have two Q functions in your ensemble, and one always wants to dive the submarine, and the other one always wants to surface. If you switch them every single time step, then the submarine will just go up and down all the time. But if you pick one and you commit to it, then you might actually see interesting behavior, like having it go all the way up for air or all the way down to shoot the fish. So the benefit of the method really comes from committing to a strategy and following that strategy for a long time. And the intuition for why that's valuable is that exploration is a problem of trying to find delayed rewards. So delayed rewards, the reason they're hard is because you have to carry out a sequence of seemingly arbitrary actions until something interesting happens. So you need to have the opportunity to carry out that sequence without changing your mind all the time. All right, let's continue. So the third class of exploration algorithms we'll cover, and the last one is methods that reason about information gain. So information gain, this is, for bandits, when we talked about this, we talked about how you can do Bayesian experiment design. You can actually figure out which action you can take to maximize the information that you will gain about some particular variable that you care about. Information gain is very difficult to compute in complex domains. So if we want to do information gain-based exploration for large MDPs, we have to make some kind of fairly egregious approximation. And we have a few choices about which approximations we can make. But before we get into that, we, again, have to answer a few questions. First, information gain about what? What is it that we want to learn about? And we have a few choices. We can say, OK, well, we want information gain about the reward function. That seems reasonable because we want to maximize rewards. The trouble is that usually if we're doing this kind of exploration, we're in a domain where the rewards are fairly sparse or fairly delayed. So information gain about the rewards itself might not be all that useful because there might just not be any actions that you can take at a given moment that will let you learn anything about the reward. The rewards will be the same for everybody. They'll only occur after a long sequence of actions. So this is by itself not that useful. Another option, which is a little peculiar but actually reasonable to use, is information gain about the state density. Now this seems a little peculiar because the state density is informed by your policy, and if your policy is changing, your state density is changing. But actually, information gain about the state density kind of makes sense. What this basically amounts to saying is, I'd like to take actions that will greatly change my beliefs about states that I'll visit. So if you see a really peculiar state, like if you're playing Montezuma's Revenge and you'll only ever seen one room and suddenly you see a different room, now your beliefs about what kind of rooms might exist in the world are very different. So that's actually a very useful kind of information gain. So even though it seems a little peculiar to change your belief about your own state density, that is in fact quite a useful thing to do. And then another one, which is maybe a little more logical, is to gain information about the system dynamics, about the probability of entering some new state given the previous state in action. And this is a little bit more directly analogous to the bandit setting. So in the bandit setting, the thetas are your model, and in here, the dynamics are your model. So this is a good proxy for learning the MDP. If you want to learn about the MDP, you want to gain information about how the physics of the world works. You want to gain information about P S prime given S comma A. It's worth saying, though, that this is still a heuristic, because finding an optimal policy in an MDP is not necessarily the same as learning its transition dynamics. So there might be some really complex transition dynamics that are completely irrelevant for actually performing the task. So it's still a heuristic. It doesn't directly translate to greater rewards, but it's a very sensible heuristic. It's saying, you know, if I'm not seeing any rewards, let's just do the thing that lets me learn more about how the world works, lets me learn more about its physics. OK, so regardless of what we choose here, it is generally intractable to use information gain directly, regardless of what is being estimated. But there are a number of approximations that we can use. So a few approximations. One simple approximation is what's sometimes referred to as prediction gain. Prediction gain is not information gain, but it's a heuristic that kind of approximates it. So remember, when we talked about count-based exploration, we talked about fitting a density model, P theta of S. And every time you observe a new state, you update that model to get a new P theta prime of S. So you update the parameters of your density model theta, and you get P theta prime. So prediction gain says, let's use an exploration bonus that is proportional to the log of the new density of a state minus its old density. And this is a reasonable proxy for how much your state density changed, because if you saw a totally different room in Montezuma's Revenge that you have never seen before, then your old density model will give it very low probability. It might give it a probability of 0, which means the logarithm is negative infinity. And after you fit a new model to that new room, then it will give it some probability is still pretty low because there's only one image of it, but it'll be much higher than it was before. So if you've never seen that room before, you might give it a probability of 0. Now maybe you give it a probability of 1 in a million. You take the logarithm of that, and you get, you get -6 minus -infinity. That's a pretty big bonus. That's a bonus of infinity. So this kind of bonus can actually effectively reward you for novelty. And it was introduced in some work by Schmidhuber quite a long time ago, and then Bellmer, the pseudocount paper, also discusses this bonus a little bit and compares to it, actually. Okay, so that's prediction gain, a kind of a crude approximation of information gain, but a fairly sensible one if you want information gain about state densities. Does anybody have any questions about prediction gain? Yes? I'll get to that in a second. Yeah, so what's the relationship between this and KL divergence? So that's going to come up in the next approximation that I'll discuss, which is going to use variational inference. So this is from a paper by Huthoft et al. Called VIME, which stands for variational something or other. And the particular connection that that paper draws on is that information gain can actually be equivalently written as a KL divergence. And it's a KL divergence between the new distribution over the model against the old distribution over the model. Now, this is not an approximation. This is actually exact. But let's, and then we're going to approximate the KL divergence. But let's drill into what this KL divergence is really saying. So the KL divergence is between two distributions over theta. Theta is the parameter, in this case, of a model of transition dynamics. So it's a parameter of a model for P S prime given S comma A. So theta is the model parameters for a model that you're learning. And you have a distribution over model parameters. So this is not just training a neural net to predict S prime given S comma A. This is training a distribution over the parameters of neural nets. This first distribution over theta is conditioned on a history. So the history is all the prior transitions you've seen so far. This is your data set. So your data set induces a posterior distribution over model parameters. And this is saying, let's condition theta on your data set H, which is your history, and a new transition that we observe, ST, AT, ST plus 1. So this thing, the H, ST, AT, ST plus 1, this is your data set plus a new transition. And the second distribution, P theta given H, this is your old distribution over parameters. This is your belief about the parameters given just your previous history. So the KL divergence is between two distributions over parameters of your model. The first distribution is given your history plus a new transition, and the second one is given just your history without that new transition. So this is measuring the difference between the distributions over parameters after having seen a new transition. So the intuition here is that a transition is more informative if it causes your belief about theta to change. If your distribution over the parameters of your dynamics model changed a lot as a consequence of seeing a transition, that was a very informative transition. So that's the intuition, and it makes sense. And this is exactly information gain. So there's no approximation here. This is exactly what information gain is supposed to do if you want information gain over your dynamics. The trouble is that this thing is intractable because this is a distribution over the parameters of neural networks. It might be some crazy thing. There might be, really, really multimodal distributions over neural nets. So it's completely intractable to actually learn P theta given H. So what you can do is you can use variational inference to estimate P theta given H with some other distribution Q theta given phi. So Q is a variational approximation. That's your variational distribution. It has its own parameters phi, and it's going to be trained to look like this posterior theta given H. So let me talk about that a little bit. And then, and of course, given a new transition, SAS prime, you'll update phi to get phi prime, and that's what will give you your KL divergence. So you want Q of theta given phi to look like theta given H. And to do that, you'll optimize the variational lower bound, the KL divergence between Q theta given phi and P H given theta, P of theta. So H given theta is easy. Like if you have some vector of neural net parameters, you can ask that neural net, how likely do you think this transition is? That's an easy question to answer. Theta given H, that's very hard. That's saying if you have this data set, what's your distribution over parameters? That's a lot harder. So This makes it easy. This scale divergence has nothing to do with this scale divergence up here, by the way. So this is just how you learn Q, and then there will be another scale divergence between Qs to actually measure the information gain. So now, how do we represent Q? So Q needs to give us a distribution over neural net parameters, and we'll have a very simple Q. We'll just say the distribution over your neural net parameters is a product of independent Gaussian distributions over the weights. So let me just draw this. I think it's a little easier if I draw it. So if you have a neural net, it takes in your state. It goes through some hidden units, right? And then there's some other hidden units up here, right? That's the neural net. Can everyone see this? And then you put them together at the end into S prime. And this is S comma A. So in a regular neural net, you have a scalar value for every weight. And now what you do is you just put a little Gaussian on every weight. You just say every weight is not just one number, it's a little Gaussian distribution. So that means that before you had theta ij for each weight, and now you have mu ij and sigma ij for every weight. So every weight has a mean weight and a variance of the weight. So it's just a little Gaussian for every single connection in your neural net. Okay, so that's how we're going to represent Q. So Q, theta given phi, independent Gaussian parameter distributions with mean phi, and phi is also going to, this is actually a typo on the slide again, there's going to be means phi and variances phi. And this particular way of approximating Bayesian neural networks is just described in this paper by Blundell et al., Weight Uncertainty in Neural Networks. So it's a very simple distribution, but it's enough to give us some notion of uncertainty about weights. And then, given a new transition, SAS prime, we're just going to update phi with gradient descent. We'll basically update it with backprop to get a new phi prime. And because KL divergences between Gaussians are easy to compute analytically, this KL divergence, so we're saying that Q approximates P, so we'll just replace the P's here with Q's. So that means our information gain is approximated with Q theta given phi prime against Q theta given phi. And both of the Q's are Gaussian distributions over thetas, and KL divergences between Gaussians are very easy to compute analytically. So this KL divergence is very easy to compute once you have phi. Okay, so this is approximating information gain with variational inference. Does anybody have any questions about this? This is kind of a lot to take in, but if anyone has any questions, we can talk about it further. Yes?
So are there a lot of drastic changes you have to do in like the individual nodes backprop, like gradient, when you...
In order to implement the weight uncertainty in neural nets. It's not that bad. So you can take a look at the paper, but you basically end up with a slightly modified backpropagation rule. And I should say, by the way, that this is just one of a number of different ways to estimate parameter distributions with a variational lower bound. Another one, that if you're interested in this topic, is something called Bayesian dropout, where you can actually use the dropout regularization technique to approximate a distribution over neural network weights. So this is one technique. Bayesian dropout is another one. You could also do all this stuff with Bootstrap, conceivably. It hasn't actually been done in the literature, but in principle, Bootstrap can also give you this distribution. OK. So we're going to use, in order to use this in an exploration algorithm, what we're going to do is we'll use our approximation to information gain, the KL divergence between the two Qs, as an approximate exploration bonus. So in the same way that we use the counts for the exploration bonus, we'll use information gain as an exploration bonus. So we'll add it to our reward with a little multiplier. Does it help? On some tasks, it helps quite a lot. So these are some little benchmark continuous control tasks. The orange line is the one that's using this approximate information gain, and the blue line is a standard algorithm that's doing random exploration. And the different rows here are different RL algorithms, and the different columns are different problems. So what are some of the trade-offs of approximate information gain? Well, it has a very appealing mathematical formulation, so it makes a lot of sense to consider actions that will let you learn more about the dynamics. It's closely related to seeking out novelty, but in some ways, it has a sort of a stronger mathematical intuition. The downside is that the models that you end up with are more complex and are generally a little harder to use effectively. So this thing with building approximate Bayesian neural nets, you have to make some kind of approximation. That approximation is usually a very egregious one because true Bayesian neural nets are intractable, and there's quite a bit of complexity that's introduced because of doing this. That said, there are a number of algorithms for exploration that look an awful lot like this information gain term, but are more heuristic and, in some cases, simpler. So this thing is approximating information gain, but if we look at its structure, what it's really doing is it's looking at the difference between the phis. So if your phi changed a lot, if phi prime is very different from phi, then the scale divergence will be bigger. So a relatively simple intuition that you might get from this is that, well, let's not worry too much about all the information theory. Let's not worry about the information gain. Let's just train up some models that predict S prime given S comma A, and let's look at how much did those models change, or how much did those models mispredict the future. And there are a number of other exploration methods that I won't cover in detail in this lecture, but that draw on this intuition in kind of a more heuristic way. So there's some work by Stady et al. In 2015. What they do in this paper is that they encode images using an autoencoder, and then they train a predictive model that predicts the next autoencoder state. And then they use the error of that predictive model, it's literally just its squared error, as a measure of novelty, because the intuition is that if the model didn't predict the next state, then the next state is probably pretty different from ones you've seen before. So let's use that as our exploration bonus. There's some work by Schmidt-Huber. There's actually quite a few papers on this, but there's a survey in this Formal Theory of Creativity, Fun, and Intrinsic Motivation. And the idea there is also to look at errors in models. And there are a few bonuses that are explored, including exploration bonuses for model error, exploration bonuses for the model gradient. So you say, if you see a new point and you get a big gradient out of it, that's an interesting point because you had a big gradient. You learned a lot from it. And many other variants. So if you want to learn about those variants, check out this survey paper. And there are actually many other works that draw on this basic intuition of saying, if you have an error in a model, that means you're seeing a new state. So they're not doing information gain, they're not even approximating information gain, but they're drawing on that intuition to build these heuristic exploration methods. OK, any questions about this? Yes?
But these are all just ways to measure how novel a new state might be, right?
Right, so these are all ways that are more than just novel. They're trying to be a proxy for whether the state allowed you to learn something about the dynamics. So if you believe that transition dynamics in your MDP are a good correlate for exploration, these are different ways to sort of approximate whether you're learning something about dynamics.
Right, but that doesn't tell you how to schedule your exploration, right?
Correct. So all of this is just about how you create that reward bonus, and then you still have to put a weight on and all that other stuff. So this has all the same downsides as the count-based stuff. All right, so some suggested readings if you want to learn more about exploration. This is a paper by Schmidt-Huber, Jürgen Schmidt-Huber on exploration. That's a little bit older, but has a lot of interesting ideas in it that inspired quite a bit of follow-up work. This is the Stady et al. Paper on model error. This is the paper that does posterior sampling for Q-learning on Atari by Ian Osman. This is the variational approximation to information gain paper. This is the count-based exploration paper that I talked about at length. And if you're interested in optimistic exploration in deep RL, I actually highly recommend this paper. They have a very nice theoretical derivation and also a good discussion of other alternative methods. And then this is the exploration method using hashing and compression that I talked about on Monday. And this is the EX2 model, the model that builds classifiers for every point to try to find whether a point is novel by how distinguishable it is from past points. OK, so that's it for exploration. In the second half of today's lecture, I'm going to talk about transfer learning and meta learning. And I think now would actually be a good time to take a break. So let's take a break for 3 minutes, and then we'll come back and talk about transfer learning.
Could we not just provide surprises or rewards, but also have a subnet of some sort to predict the surprise?
Mm-hmm. Yeah, so this is a good question. And what your question is really getting at is that you don't just want a policy that will greedily take the most surprising actions, but will actually plan for surprise. The exploration bonus has actually already accomplished that to some degree, because we're not actually choosing actions based on maximum surprise. We're adding the surprise to the reward, which means that when you then train a Q function, it will actually plan for future surprise. And that's actually important, because if you just greedily choose information gain actions, that's not going to be nearly as effective as adding it as an exploration bonus. So you're essentially already planning for it to some degree.
But the next time we do that action, we won't get the surprise. So to
Right.
build it into the Q function seems a little bit off for the next time.
Well, yeah, so you're relying on your RL algorithm being good at planning, essentially. So what RL algorithms learn to do, you can view what they're doing as learning to plan, essentially. They see a sequence of experience with some delayed rewards, and they're figuring out which actions they should schedule in order to achieve those rewards. So if you believe your RL algorithm is good, then adding your exploration bonus to the reward is reasonable. If you believe your RL algorithm is too slow, then maybe there's a better way to do it. In model-based reinforcement learning, people have looked at something like what you said, where they've looked at actually optimistic planning. And there, one of the things that's very popular to do is not actually to change the reward function, but to change the dynamics. So what they do is they say, okay, if you have uncertainty about the dynamics of the system, you're going to do model-based RL, which means you'll plan through your dynamics. What you'll do is you'll actually do optimistic planning. So you'll say, if you're unsure about the dynamics, don't assume it's random chance, assume that you get to pick. So if I think that, oh, if I play the lottery, I might win or I might lose, assume that you'll win and plan accordingly. And that'll get you an optimistic plan. All right, let's continue. So in the second half of today's lecture, I'll start talking about transfer learning, and then we'll wrap this up next week. So in transfer learning, we're going to look at the benefit of sharing knowledge across tasks. We'll talk about the transfer problem in reinforcement learning, and transfer learning with a single source and target domain. And then next time, we'll also discuss multitask learning and meta learning. So the goals of this part of the lecture will be to understand how reinforcement learning algorithms can benefit from the structure in prior tasks, and understand a few different transfer learning methods in the literature. So this lecture is a lot more going to cover basically cutting-edge research. So a lot of these things are not necessarily methods that have been around for a while. They're pretty new, and I'll just discuss the strengths and weaknesses of some of them to give you some idea of the trade-offs. But keep in mind that this is not a solved problem. This is something where there's just sort of a few initial ideas, a few papers here and there, and a lot of open questions that still remain. So let's go back to this example of Montezuma's Revenge that I talked about on Monday to motivate the discussion of exploration. The reason that Montezuma's Revenge is not such a difficult game for us when we play it as ourselves is that we actually understand what these sprites mean. So to us, we bring to bear all of our prior knowledge. We understand that keys open doors. We understand that ladders are things that we can climb. And while we might not understand what the skull actually does in the game, we kind of know that skulls are not a good thing. Like, we know that the skull is probably not going to be your friend. It's not going to help you win the game. It's something negative. So there's our prior understanding of problem structure, our prior understanding of symbols and features and so on, helps us solve complex tasks much more quickly. And it's awfully appealing to think about whether it might be possible to get our reinforcement learning algorithms to also work much more efficiently, learn much more quickly, and overcome really difficult exploration challenges by drawing on prior knowledge that they might have gained at other structurally similar tasks. So can reinforcement learning use the same prior knowledge as us? If you're trying to play Montezuma's Revenge, can you use your past experience of robbing tombs to help you figure out how to play the game? If we've solved prior tasks, we might acquire useful knowledge for solving a new task. But then the question is, how is this knowledge stored? How do we represent that in our deep RL algorithm? And we have a number of different options that we can explore. We can store our knowledge in something like a Q function or value function. That's quite nice because a Q function or value function tells us which things are good. So if we don't, for example, necessarily understand how to grab the treasure in Montezuma's Revenge, but we understand something about treasure being good, then we might more quickly recognize, if we grabbed it by accident, that this is something we should repeat because we know treasure is good. We can encode prior knowledge in a policy. So a policy tells us which actions are useful. So if we initialize with a good policy, in many cases we might do something sensible. If you want to drive your car to navigate to the grocery store, initializing with a policy that drives the car on roads rather than crashing into buildings, it will probably greatly simplify the problem, because then you'll avoid a lot of really useless actions that are not useful for driving a car, regardless of what you're trying to accomplish. So some actions are just never useful, and if you have a prior policy, that can really help you rule those out. You can encapsulate prior knowledge in a model. A model is a very appealing way to encapsulate prior knowledge. So model here means dynamics model, because a model is knowledge about the problem that is independent of the task you're trying to accomplish. So especially in physical environments, the laws of physics are going to govern objects in the real world, regardless of where you are in the universe. So if you have a really solid understanding of the laws of physics, encapsulated in your model, that's something that you can take with you to then solve new tasks. And then the fourth one, which is a little bit less obvious, but still very important, is features and representations. So features and representations can really help us learn, especially when we have complex observations like images, not by telling us what to do, but just by transforming the observation into a format that is more suitable for decision making. This is a little bit less obvious, but let me show you a little experiment that studies this. This is borrowed from Evan Schellhammer's work called Loss is Its Own Reward. And in this paper, what Evan did is he tried to study the value of representation in Atari games. So these plots, they show two different learning curves. The black one is just what you get if you run your standard reinforcement learning algorithm. The red curve is formed by doing the following kind of peculiar procedure. Evan trained policies for each of these tasks to convergence, and then he cut off the last layers of the policies and just left the convolutional layers. So the intuition behind what that does is it preserves the representation, but removes all of the decision-making ability, because the convolutional layers, they're tiled over the image. They can't possibly be deciding what to do by themselves, but they give you a good representation. So the red curve is what you get if you initialize the convolutional layers from a successful policy, but relearn all the fully connected layers from scratch. And you can see that the red curves are much, much better, especially on Sequest. It just jumps right up and gets to good performance. So this suggests that getting the right representation greatly simplifies the problem that the reinforcement learning algorithms aim to solve. So this is kind of a cheating experiment. This is just meant to test, if you have the perfect representation, does it help? And the answer is very much yes, it does. So representations could conceivably be an effective way of doing transfer. OK, so the problem of transfer learning, there are a number of ways you can define it. One reasonable way to define it for the purpose of this lecture is to say it's using experience from one set of tasks for faster learning and better performance on a new task. So in RL, a task is an MDP. So that means that you learned on one MDP or a set of MDPs, and now you want to learn a new MDP faster or better by using something you learned before. So if your MDP before was robbing the tomb for the treasure, now maybe you can do better at Montezuma's Revenge. So typically, the task that you trained on before is called the source domain, and the task that you're trying to solve now is referred to as the target domain. And sometimes there might be more than one source domain. So in today's lecture, we'll talk about the case where there is just one source domain, but next week we'll also talk about multiple source domains. And there's a little bit of terminology that's often used in transfer learning that I can introduce on this slide. So if you see someone use the word shot, you say 0 shot, 5 shot. That means the number of attempts that you get in the target domain. So if someone says 0 shot transfer learning, what they mean is train in the source domain, don't try anything in the target domain, just go and act, and that's your test time, and you're just supposed to succeed without learning anything else. So 0 shot means you haven't gotten any chance to try anything in the target domain. You're just supposed to jump into it without knowing anything and succeed. And sometimes you can do that. 1 shot means you try the task just once. So if you have an episodic problem, maybe you have a robot trying to assemble some blocks together, the robot gets to try assembling just once, and from that it's supposed to then be able to succeed. And then few shot means try it a few times. And typically transfer learning methods will be attempting to do some of these things. They'll either be trying to learn with a small amount of experience, or they'll just attempt to get better overall performance with a lot of experience, just to see if they can do better than if you were learning from scratch. So this is a little bit of terminology that you might see in papers on transfer learning that's good to know about. OK, so how can we frame transfer learning problems? There are a number of choices that we have, and we'll talk about some of these today and some of these next week. So one of the things we can do is we can formulate a kind of a forward transfer problem where you train on one task, and then your job is to transfer and do well on a new task. So there are a few ways you can do it. One of the ways you could do it is you just try it and hope for the best. So train on some source task, hope that it's a good source task, and just run in the target domain and hope for the best. So there's no technique there, but you can try it and see what happens. You can try to think of more clever architectures. So there are some architectures that might actually facilitate transfer, and we'll talk about one example of these, which are called progressive networks. And that's often done in combination with fine-tuning, where you train on a source task and then you train some more on the target task in this kind of stage-wise manner. If you're allowed to play with the source domain, if you're allowed to actually choose what the source domain is, there are a number of design decisions that can greatly increase your chances of successful transfer. And one of them is how much diversity there is in the source domain. So we'll talk about the effect of randomization on transfer. If you transfer from many domains to a single domain, there's actually a lot more interesting stuff you can do. So we'll have another section, this will probably actually be next week, on multitask transfer, where you train on many tasks and then transfer to a new task. And there's a lot more interesting stuff you can do here. You can think about model-based reinforcement learning, where you look at multiple different source domains, try to extract a representation of physics, a representation of the dynamics of the system, and then take that to a new target domain. You can do what's called model distillation, where you actually try to train on multiple source domains and then use supervised learning to distill that experience into a single behavior that is more generalizable. You can train contextual policies, which are policies, when you train a single policy for many tasks that takes the task identity as an input. So you have one big neural network and it's told, now you're doing this task. And then you can actually train networks that are modular, that have reusable parts, some of which are used in some tasks and some are used in others. So we'll talk about that a little bit more as well. And then the third thing that we'll talk about, and this will definitely be next week, is multitask meta-learning. This is also multitask learning, but here instead of trying to learn a representation like a Q function or policy, you're instead trying to learn how to learn. So you're actually using those past tasks to learn something that will actually explicitly accelerate future learning, such as an optimization procedure or a representation that can fine-tune more quickly. So we'll talk about meta-learning based on recurrent neural networks and then gradient-based meta-learning. So this will be also next week. So one thing I would emphasize is that the reason this is such a long list is because there is no single solution that just works. So what I'll actually be presenting is a survey of various recent research papers, because transfer learning is still very much an open problem, and there are a number of techniques, a number of results for those techniques, but in the end it depends heavily on your particular problem setting, what you're trying to do, and which of these things you'd like to try extending or using. So this is, keep in mind this is more of a survey, not necessarily a lecture about, this is the technique that should be used for everything. All right, we already had a break, so let's talk about the first part of this discussion, which are the forward transfer methods. And these are methods that train on one task and then try to transfer to a new target domain. So you can try it and hope for the best. This is not a method, this is just a thing to try. If you have a target domain, you believe it's close enough to your source domain, well, learn something in the source domain and just see what it does. Sometimes this works, but there are no guarantees. So here's a little illustration. We can have, I think I showed this video before when I talked about model-based RL. You can have a robot that learns to do a task like putting a cap on a bottle. And then you can give that robot a slightly different environment. Maybe now there's some bottles in the background, so the images look a little different. There's some distractors, and sometimes it'll work. It'll work up to a point, but the trouble is that because you didn't do anything special for transfer learning, you can't really guarantee that it will work in that new target domain, and it's sort of arbitrary how well it'll work. So if, for example, in this case, somebody's holding the bottle and the sleeve of their shirt is the same color as the robot's arm, it gets kind of confused because it's never seen things like this before. So line transfer sort of succeeds based on chance. And here's another illustration from another recent paper that shows some interesting examples. So here the robot is pouring almonds from this bottle into a cup. And it's doing very well. It's generalizing to lots of different cups until it sees the cup that's a little too unfamiliar, and then it just gets confused and pours the almonds right between two cups, because this is a situation that's just different than it's seen before. So forward transfer doesn't always work. It's sort of based on chance. So we can do something to stack the odds in favor. One of the things we can do that is very, very simple is just fine-tuning, meaning you train something on your source domain, and then you train it some more on your target domain. Fine-tuning is basically the most popular transfer method in regular supervised deep learning. And there are some really simple things you can do that work almost shockingly well. You can take a large data set like ImageNet, you can train a big convolutional neural network on ImageNet, you can throw out the fully connected layers, keep the features from the convolutional layers, and then solve completely different visual perception tasks using those features, and very often that works very well. So something about big data set, relatively general purpose task like classifying 1,000 classes gives you good features in supervised deep learning. The trouble is that there isn't such a thing as ImageNet features in reinforcement learning. So in reinforcement learning, when we have to actually carry out complex behaviors, we don't know how to do this. We don't know how to get the perfect ImageNet features that will just work very well in many, many different cases. We can still try to do fine-tuning, but it takes a lot more care. So there are some challenges with fine-tuning in reinforcement learning. RL tasks themselves are generally less diverse. So having the little ant, this is maybe something you guys tried in homework 1, having the little ant running forward, it's not really very representative of what needs to happen if that ant needs to jump. Like, the task is not very diverse. It's not 1,000 different ant behaviors. It's just one thing. It's just running. The features that you get as a result are generally less general. They're less suited for other tasks. And the policies and value functions that you get become overly specialized. So if the ant can run a little bit faster by sacrificing some of its robustness, some of its diversity, it'll do that because all you're rewarding it for is running fast. So when you over-specialize to one thing like running really fast, that will come at a price of all the other stuff because you don't need all the other stuff. There is another issue, which is that a little more subtle. Optimal policies in deterministic Markov decision processes are deterministic. Or it's actually backwards. A determinist, there's always an optimal policy for a fully observed Markov decision process. It should be not deterministic. So if you have a fully observed Markov decision process, I apologize, there's a typo there. If you have a fully observed Markov decision process, there always exists an optimal policy that is deterministic. And if you have a policy that's deterministic, and you initialize from that and then fine-tune, that's a bad thing, because now that deterministic policy is not exploring anymore. It's not trying to learn anything. It's just doing the same deterministic behavior over and over again. So you get loss of exploration at convergence. This is a very well-known issue with policy gradient methods, for instance. And low-entropy policies adapt very, very slowly to new settings. So if you just naively train a policy with policy gradient, and then you transfer it to a new target domain, you might find that it's just not learning anything simply because it has lost all of its exploration capacity. It's become almost deterministic. So there are a few things that we can do to actually address both of these things, both the diversity and the entropy, the exploration. And the way that we can do this is actually using a technique that I covered before when I talked about control as inference. So when I talked about control as inference, one of the things I mentioned is that the policy that you get when you do inference in this graphical model can be shown to be equivalent to a policy that maximizes the expected reward, which is our usual RL objective, and also the entropy. So that is a maximum entropy policy. And that has very interesting implications when it comes to fine-tuning. So if you're maximizing the reward and the entropy, what you're essentially doing is you're asking the policy to solve the task in all the possible ways. So if you want to go around the tree, and you can go around the tree successfully by going left or by going right, learning to do both of those things will increase your entropy. So the maximum entropy objective encourages you to discover multiple ways of solving a task. And learning multiple ways for solving a task is very good for fine-tuning. So let me illustrate this with an example. Let's say that you have this little quadruped robot, and the quadruped robot needs to get over here to this little blue cross. It can get there in two ways. It can go up or it can go down. If you just maximize reward, it'll probably learn to go down because it's a little shorter. Or go up, sorry. It'll go up because it's a little shorter. But if it takes the lower passage, it's about the same length. It's a little longer, but it gets higher entropy. So maybe if you have the entropy maximization, it'll learn both going up and going down. And now, if you want to transfer to a new domain, let's say in your target domain, it's very similar, but now there is a wall over here. If it already has both behaviors, if it randomly chooses to go up or down, that's a much better spot from which to fine-tune it, because half the time it will actually succeed at this new task. But if you had a regular reinforcement learning policy that over-optimized for the shortest path, when you then fine-tune in this new domain, that's as bad as starting from scratch, because all it ever does is fail. So in this case, maximizing entropy greatly helps with your ability to fine-tune. So learning to solve a task in all possible ways provides for the most robust transfer. And in fact, this connection between robustness and maximum entropy can actually be made formal in certain optimal control settings. So if you're interested in learning about that, check out Brian Zebart's work on maximum entropy models for RL. So this is a video that I actually did show before, but I wanted to show it again just to emphasize this point. So here, it's going to be a little different than that maze example I showed before. Here, what we're going to do is we're going to train with maximum entropy. That's the one on the right. And we're going to train the ant to walk in any direction. So the reward during pre-training is going to be maximize your walking speed regardless of where you're going. And with maximum entropy, it does exactly what you expect. It walks in all possible directions because that's how it can maximize its entropy. And once you have this policy that walks in all possible directions, that serves as a much better initialization for learning to walk in one particular direction. So then what you can do is you can put the ant in a hallway. It gets reward for moving down, moving south. And then on the left, you see the ant initialized from scratch. In the middle, it's initialized from a deterministic policy. And on the right, it's initialized with maximum entropy. And all of them make progress as learning progresses. So this is the 100th epoch. But the one that's initialized with maximum entropy learns fastest. It gets further sooner. Because it already knows how to walk in all possible directions, it just has to figure out which direction you want. Whereas the others this one has to learn everything from scratch, and this one has to unlearn whatever arbitrary thing it has in order to adapt to a new direction. And then if we look at the quantitative results, they also reflect this. So the blue curve is the learning curve for fine-tuning after pre-training with maximum entropy. So you can stack the odds in your favor for fine-tuning if you pre-train for greater diversity. Now, OK, does anybody have any questions about maximum entropy and fine-tuning? OK, yes?
So I guess, for maximum entropy, is it only applicable for, I guess this says it used on Q-learning. Is it applicable to, like, policy gradient? Or
Yeah, so you can actually formulate maximum entropy policy gradient methods. It's actually very straightforward. So the equation here with the entropy term, you can actually compute the policy gradient of that, and all it ends up being is subtracting log pi from the reward, which makes perfect sense. It's like saying if you have some action that's very high probability, that's lower reward because it's low in entropy. In policy gradient, this is a very, very old trick. So actually, the original reinforced paper in 1991 actually describes something very similar to this. And this is a very, very commonly used trick to encourage exploration. One caveat is that there are two parts to maximum entropy. There's the actual entropy part, and then there's the representation. So if you're doing, let's say, continuous control, and you have conditionally Gaussian policies, you can maximize their entropy, but they'll still be Gaussian. So in the example where you have to go around the tree either left or right, a Gaussian unimodal policy can't actually represent both of those behaviors without crashing into the tree. So you need both the maximization of the entropy and the ability to actually represent those high entropy policies. In discrete action spaces, it's a lot easier, because there you can represent any distribution tractably. As far as trade-offs for entropy maximization for fine-tuning, one of the things that is perhaps worth saying is that maximizing entropy does reduce your average reward, because it's an additional term added to your objective. So your performance on the pre-training domain will be necessarily worse, because you're asking the policy to maximize reward and do something else. So the downside is that you're worse in the source domain. The algorithms are a little more complex because they have to deal with these terms, and the right representation for a maximum entropy policy might not be as simple as for a unimodal policy that just becomes deterministic at convergence. So there is also a price to pay for this. There is another issue with fine-tuning that we can address with a little change in the architecture. So here's another issue with fine-tuning. Deep networks work best when they are very big. So if you want to learn something very complex, you probably want to use a big network. And bigger networks tend to do better because they can represent more functions, and they're actually often easier to optimize because the resulting space has fewer spurious local optima. When we fine-tune, we typically want to use as little experience as possible because we'd like to transfer quickly. So having a small amount of experience and a big network is bad news. So thinking back to your machine learning course, if you have very little data and a very large number of parameters, you're going to have very bad overfitting problems. So the two things that we want out of transfer, big networks to represent complex behaviors and small amounts of data, that is bad news for learning. So can we somehow fine-tune a small network, but still pre-train a big network? Right? We'd like to somehow not have this overfitting during fine-tuning, but we'd like to still have the benefit of having a big network. So one idea is don't fine-tune the whole network, just fine-tune a little bit. So let's say that you have some Atari game, and you have a big convolutional tower on top of it extracting representation, and you have like maybe a big fully connected layer, and then on top of it you have some other small fully connected layer. Well, maybe we pre-train the whole thing, but let's fine-tune just that little layer. Maybe that's enough, because that has a small number of parameters, so it won't overfit as badly. The trouble with that is that it has very limited expressiveness also. So there might not be that many things we can change about the policy by only changing the small layer. So maybe we need to change the policy in some very complex way. Maybe we need to tweak the representation a tiny bit, tweak this layer a little bit, and then tweak this layer a little bit. And that we can't do if we restrict ourselves to fine-tuning only the last layer. And the other thing is that if we do let the gradients flow through the whole network, then the big error gradients up at the top, when we first start fine-tuning, when we don't know how to do the problem, they might actually wipe out the nice initialization further down. So if we fine-tune just the last layer, then we have limited expressiveness. If we let the gradients fall all the way down, we might actually wipe out our good initialization, and we might also overfit. So another idea that we can explore is, instead of fine-tuning just a subset of the network, what if we add entirely new layers for our new task? So if we say that, OK, we can handle this many parameters, we can actually freeze all of the old layers. So those can be big and they never change, so there's no overfitting. And then we can add new layers for our new task. So this is an idea described in a paper called Progressive Neural Networks, and it works like this. Let's say you pre-trained on one game, and now you'd like to figure out how to play another game. You give it images from your new game now, so this no longer exists. This is gone. The weights in the old network are fixed, but now you have new layers over here that are smaller, and they're going to get the outputs of the old layers as input. And we add these at every layer. So we might say, OK, we'll add a smaller version of this conv tower that gets the image. We'll add a smaller version of the FC layer that gets the old conv tower and the new conv tower. And we add a smaller version of this fully connected layer that gets the old fully connected layer and the new one. So the nice thing about this kind of architecture, and then of course the last one is outputs the policy. The nice thing about this kind of architecture is that you still get the benefit of the pre-trained layers. Their weights are not wiped out because they're not changing, they're frozen. But you can still flow information all the way from the input to the output through a smaller set of learned layers. So if the old conv tower wiped out some piece of information that you really need for this new game, you can still recover it through the new conv tower, which is smaller and still trained end-to-end. So this is a method called progressive neural networks. Does anybody have any questions about this? OK. So now a reasonable question to ask is, well, does it work? How much help do you get from doing this over fine-tuning? And the answer is sort of. So it kind of depends on what you're doing, your problem setting, and the details of how you implement this. So this is the evaluation from the Progressive Networks paper. The different baselines, the first one trains entirely on the target task. The second one is the one that I said before that, the second one trains on the source task, fine-tuning. The third one, and freezes the early layers. So this is what I said before, where you freeze the early layers of the network. And the third one pre-trains on the source task and then fine-tunes on the whole network. Baseline 4 is a little peculiar. I won't get into that too much. But the thing to note here is that if you look at the median, for example, generally the progressive network, which is these bottom 3 rows, they're better, but they're not better by much. So there's like the third baseline is generally actually pretty strong. So you do get benefit over regular fine-tuning, but it's a little situational. Yes?
Would it be better just because they had more nodes in their network?
They do actually get at this in their evaluation. So I don't remember exactly how they address this question, but they do control for the number of parameters. That's generally a very good question, though. Anytime somebody says, oh, I'm fine-tuning or I'm transferring, asking them whether the number of parameters is fair in their comparison is an important thing to ask. Yes.
What about also the number of steps they take?
Yeah, so this is for the same number of steps. And they have learning curves in the paper, too. I just didn't want to show them here because they're kind of messy.
Sure.
Yeah, so this is in terms of number of steps, this is a fair comparison.
I guess my question is, like, what about if the gain isn't so much like the features, like the specific features that the old networks got, but just that they had gone from, you know, random crap to something. Like, you know, just if you just took those steps and
yeah. So, and that would often be the benefit in a fine-tuning like procedure. The thing is that you get that benefit from just naive pre-training here too. So if you just want to start with something rather than nothing, the naive pre-training is actually, it's not a weak baseline. It's actually for these tasks it's okay.
Oh, right, okay.
Right. So this is not meant to be an evaluation of fine-tuning. This is an evaluation of progressive networks in particular.
That makes sense.
There's also some nice results with progressive networks for real-world robotic tasks. So here, this is a simulation. This is a real robot, and it's trying to reach for this red square. This you can also check out in the paper, comparing the blue lines are showing two different progressive network implementations, and the yellow one is standard fine-tuning. And you can see they sort of start out strong, but this one diverges a little bit, which kind of makes sense. If you're learning from a small amount of experience, then having a large network might give you some overfitting issues. Okay, so this is progressive networks. It tends to alleviate some of the conceptual issues with fine-tuning. Not obvious how serious these issues are in practice. So in practice, good thing to think about, but important to understand whether it's really the biggest issue in your particular transfer learning problem. Okay, so let's summarize the discussion of fine-tuning. We talked about how you could just train in your source domain, test in your target domain, and hope for the best, which sometimes works, but there aren't any promises. You can try fine-tuning, which means that you pre-train in the source domain, then train some more in the target domain. There are a few issues with naive fine-tuning and reinforcement learning. Maximizing entropy can help. So maximizing entropy can ensure that you don't get stuck in just a single way of doing the task, and you maintain high entropy in your policy so that you keep exploring. We talked about how you can design architectures that are specifically well-suited for fine-tuning, specifically progressive networks, which address some of the overfitting and expressivity problems basically by construction, by the design of the network. But what if we had a little bit more control over the source domain? So what if we could actually choose the source domain to enable transfer? So far, our source domain and target domain were fixed. So for example, for the little ant, maybe he was learning how to run in the empty room, and he has to succeed in the hallway. But sometimes, when we want to do transfer, we might actually be able to manipulate our source domain to make it better suited for transfer. So what if we can design the source domain however we want, and we have a really difficult target domain? So this is often the case if you're considering training in simulation and then transferring to the real world. Typically, the simulation is something that you can design yourself, you can modify it however you want, but the real world is what it is, and it's typically quite hard. So the idea is going to be that more diversity at training time is going to enable better transfers. Just like with maximum entropy, if you see more variability during pre-training, it'll enhance your ability to transfer. The story here is going to be the same. If you get to manipulate the source domain, making the source domain more diverse is often going to be very helpful for transfer. And here I'll just talk about a few experiments that have studied this question. So the first work I'm going to discuss is called EP-opt by Rajeswaran and collaborators. And this work looked at robustness to variability in physical parameters for deep reinforcement learning kind of benchmark tasks. So for example, in homework 1, some of you might have tried the hopper task. The hopper is a monopod hopper in 2D. And what this paper explored is if during training, the hopper is maybe a little heavier, a little bigger, or a little smaller, and then at test time, it's the original hopper. So how can you change your training time source domain so that at test time, your hopper can hop regardless of its weight or regardless of its friction coefficient and so on? So the discrepancy here between the source and target consists of the physical parameters of the hopper. And the idea is very simple. A fat hopper is not going to be able to hop if it becomes thin, because that policy is going to be very narrowly specialized to high weight hopping. But if you train on a variety of different physical parameters, you actually get more effective generalization. Now, this might seem kind of obvious, but some of the analysis is actually, I think, quite elucidating as to the nature of this transfer. So if you train on more varied physical parameters, you generalize more effectively to parameters that you haven't seen before. And in fact, OK, so this is what these plots are showing. So here, the x-axis is variability in torso mass during training, and the vertical axis is the torso mass at test time. So you see for m equals 3, training close to 3 works best. For m equals 6, obviously training close to 6 works best. So that's what we already knew. If you train on an ensemble, if you train on a variety of masses, you actually get very good performance for all the masses between 3 and 9. That's a huge range. That's a factor of 3 range. And the interesting thing is that the performance here, if you look at the vertical position of this bar, is about the same as if you train on the right mass. So this is if you test on 9, you train on 9. And this is if you train on ensemble and test on various masses. And this is a little surprising because generally the conventional wisdom, for example, in robust control is if you train under greater variability, you will get more robustness at the cost of task performance. The interesting thing about deep reinforcement learning is that, in general, that might still be the case, but the greater expressivity of the policy alleviates this to a substantial degree in some cases. So the reason that you get good performance across a range of masses, or at least part of the reason, is that the policy is powerful enough to represent strategies that are good for different masses without necessarily sacrificing performance in any one condition. And if you're interested in what the distribution of the ensemble looks like, here it's this Gaussian curve. So it's sort of centered at 6 and falls off towards 3 and 9. So the interesting thing is not that training on multiple masses helps you generalize to masses. The interesting thing is how much it helps and also what your performance is. So over here, you've barely seen the 3, but you're still doing pretty well there. The other thing that's kind of interesting in the analysis in this paper is the robustness to unmodeled effects. Basically, the story here is that the more you randomize the physical parameters during training, the more likely you are to succeed when at test time there's a new physical phenomena that you did not vary. So part of the intuition here, for example, is that if you train to hop with different masses, and then at test time you have a different friction coefficient, well, a lower friction coefficient looks an awful lot like a lower mass when it comes to the corresponding physical behavior. So the more you randomize at training time, the more likely you are to then succeed, even when there's an unmodeled effect that's introduced at test time. And this is a big deal because oftentimes the issue with simulation to real-world transfer is not that we can't vary the parameters that we do have. It's that we just don't have the parameters to simulate some unmodeled effects that happen in the real world. So if you're simulating a robot in Mujoko you have a friction coefficient. In the real world, you have a static and a dynamic friction coefficient, which you don't have in Mujoko. So static friction is not simulated. Therefore, you get static friction in the real world. You might be in trouble. So part of the kind of empirical result described in this work is that maybe if you vary enough parameters in the simulation, you can actually mitigate the unmodeled effects. So this is still kind of an empirical result. There isn't any guarantee, but maybe some insinuation of this. And then the other thing that's explored in this paper, for those of you that are interested, is actually closing the loop and adapting. So if you do get a little bit of experience in the target domain, you can go back and adapt your source domain distribution. And there, the interesting thing is that you want to adapt your source domain distribution in a way that preserves the diversity. So you want to bring it closer to the target domain, but not necessarily at the cost of removing the entropy of that parameter distribution. And I'm not going to get into that too much, but if you want to learn more about it, you can check out the paper. So this is randomizing physical parameters to enable better transfer. OK, so I think that's it for today. When we come back next week, I'll talk about randomization for transferring visual policies and also multitask transfer learning.